boundary between two materials. This is air, and this is water. Here you have your incident beam, which part of it's going to be reflected and part of it's going to be refracted. Okay, and then you have a normal, which is going to be perpendicular to your surface, also called your optical axis. So your first angle here is theta 1, which is going to be your angle of incidence. Here is theta 1 prime, and that's going to be your angle of reflection. And then down here you've got your theta 2, which is going to be your angle of transmission, also called refraction. The light that's refracted can be explained by Snell's law of refraction. Which says N1 sine theta 1 is equal to N2 sine theta 2. And here the N's are your index of refraction, which is equal to C over V, where V equals your velocity of the speed of light in a vacuum. And your V is the speed of light in your medium. Okay. The index of refraction for water is equal to N equals 1.33. And the index of refraction for air is equal to 1.00. Next we need to define what we call a critical angle, which is going to be the minimum angle at which all light is reflected. This is the limiting case though, so when N1 is greater than N2, then theta 2 is going to be 90 degrees. So your critical angle should look something like this. And then the calculation for the critical angle is going to be is equal to N2 sine of 90. Which is going to give you sine of 90 is 1. So then you'll have and then to solve for your critical angle, the inverse sine of N2 over N1. So in our example, our N2 is air. So we'll do this. N2 is air, which is going to be 1.00 over 1.33, which is the index of refraction for water. And that's going to give us our critical angle of 48.7 degrees in our experiment. Okay, so what this whole experiment is about is total internal reflection, which occurs when light encounters the boundary between a medium of a higher index of refraction, which is your water, and your lower index of refraction, which is your air. And then that's when your angle of incidence is greater than, your angle of incidence is here, is greater than or equal to your critical angle. So in our experiment, the laser is going to be in the more dense medium, and it's going to be heading towards a less dense medium, which is your air. Being at angles of incidence greater than the critical angle, the light never actually leaves the stream of water. In fact, the stream of water is going to act as a light pipe to pipe the laser beam along its trajectory. So what I'm saying is that here's our water coming out of the 2 liter. We're going to have air out here. And our laser is actually going to be trapped inside this water, and it's going to bounce, and it's going to be reflected throughout the light, which is going to be why it follows the water all the way down into our bucket.